Hello guys, how is it going? This is Mike coming back at you here with another video on number theory. In the previous video, we wrapped up chapter 2 and we saw some more sample problems about solving linear Diophantine equations. We saw that some of them we could solve and some of them we could not, and we ran through the process as to how do you find the particular solution and then use values that you found to come up with the general formulas for all solutions to the given equations. In this video, we're going to begin chapter 3. We're going to kick it off with the fundamental theorem of arithmetic, and we're going to see how we can use this theorem to talk about certain ways that we can write numbers, and then see how we can take this new way in which we write numbers to come up with an easier way to come up with our GCD and LCM. And we can do this with even larger numbers, like 6 digits, 7 digits, 8, anything like that. But before we get into the actual statement of the fundamental theorem of arithmetic, we need to define some terms, and we need to talk about some smaller facts that will get used. So recall the definition of a prime number. You've all heard of prime numbers. An integer p greater than 1 is prime if its only positive divisors are 1 and itself. Note that we specify here that p is strictly greater than 1. You always hear the big controversy, oh, well, is 1 a prime number or is it not? No, 1 is not a prime number. We are not considering 1 to be prime here. It has to be greater than 1, and its only positive divisors are 1 and itself. Here's a couple smaller facts that we need to state first. 1, if p is a prime and p divides the product of two numbers a or b, then p has to divide either a or p has to divide b. And if you just stop and think about this for a second, it shouldn't take too much time to see that that really does make sense. If it's going to divide the product, then it has to divide one of the factors in that product. Number 2 just shows that number 1 generalizes to the product of any number of things. If p is a prime and p divides any product of numbers, then p has to divide one of those numbers that are making up that product. 3 is very similar to number 2, but a little bit different. If p, q1, q2, q3, ... all the way up to and including qn are all primes, and p divides the product of the q's, so p divides q1 times q2 times q3 times qn, then p has to be equal to one of those q's. P has to be one of those primes there. And these 3 small facts would get used in the proof of the fundamental theorem of arithmetic. We're not going to go through the proof of this here, but we are going to use some of these facts in the next section when we talk about the proof of a very important fact regarding prime numbers. But here we just state the fundamental theorem of arithmetic now. Every integer n greater than 1 is either a prime or is a product of primes. This representation is unique up to the order the factors are written. So what this is saying is you give me any number greater than 1. That number is either a prime, or I can find prime numbers that will multiply out to give you that number that you told me. The second part of this representation is unique up to the order the factors are written in. So really what this is saying, and just going with a very basic sample here, 105 is 3 times 5 times 7. This is also 5 times 7 times 3. It's also 7 times 3 times 5. And there's other ways that we can write that combination. When they say this representation is unique, they mean there is no other number that can be written as a product of 1, 3, 1, 5, and 1, 7. 105 is the only number that can be written as a 3 times a 5 times a 7. The up to the order the factors are written in part means that saying 3 times 5 times 7 as opposed to 5 times 7 times 3 doesn't mean that we're talking about two separate numbers here. They're both talking about 105s, but just the order in which we write the factors does not matter, which we all know because we've heard that many a time when we've done multiplication. It is possible that we have the same prime occurring more than one time in a particular number. For example, the number 5400. If you write this out as a product of primes, you get 2 times 2 times 2 times 3 times 3 times 3 times 5 times 5. And instead of writing 2 times 2 times 2 out, we could just write 2 cubed. And instead of writing 3 times 3 times 3, we can just write 3 cubed. And instead of writing 5 times 5, we can write 5 squared. So we can write that same number, 5400, as 2 cubed times 3 cubed times 5 squared. And there's a special form that we call this right here. When we take a number and we write it as a prime raised to some power times another prime raised to some power times another prime raised to some power, and going up and keeping with that pattern. Any positive integer n that's greater than 1 can be written uniquely in canonical form. So that's what this guy is right here. It's in the canonical form, which is when you take a prime, you raise it to some power times another prime, and we typically write these primes in ascending order. So P1 to the power K1 times P2 to the K2, where P2 is greater than P1. Then you'd have times P3 to the K3. P3 would be greater than P2. And you keep going up with this until you have your final prime that shows up raised to some power for that particular prime. Every one of the powers there, every one of those k's, is a strictly positive whole number. We don't write zeros, and we're not going to have exponents that are negative. So here's just a couple more samples of numbers being written in canonical form here. These are a little bit harder. 10,020, you can write as 2 cubed times 3 times 5 times 167. 167 is a prime number. And then you have 69,459 is 3 times 13 squared times 137. So those are just a couple more samples of things being written in canonical form. But you see that we have the primes listed in increasing order in each of these. Each of these primes has a positive power to it, nothing raised to the 0 power, nothing being raised to a power that is negative. And with canonical forms, we now have another method of finding the GCD of our two numbers A and B. So between A and B, you're going to have a a collection, or you are going to have certain primes, P1, P2, P3, all the way up to and including Pn. And between these two numbers, A and B, each of these primes divides at least one of A, or it divides at least one of A or B. And for this one particular usage of it, we do allow exponents to be 0 in the case that a prime shows up in the canonical form of one number, but not the other. So allowing exponents to be 0 when it is appropriate, we can say that A has a canonical form P1 to the K1 times P2 to the K2 times Pn to the Kn. And then B has canonical form P1 to the J1, P2 to the J2, ... Pn to the Jn. And we give separate names to the exponents because they don't necessarily have to be the same in each number. These can logically and sort of obviously be different values. Then the GCD of A and B is P1 to the R1 times P2 to the R2 times Pn to the Rn. Now, what are these R's here? Well, R sub I is the smaller of the exponents associated with that prime in the canonical forms of A and B. So R sub I is the minimum of K sub I and J sub I. So R1 here, to figure out what R1 is, I would look at what K1 is and what J1 is. And I'd take the smaller of those two numbers, and that would be the exponent on this prime P1. Move over to my next exponent, R2. I'd look at K2 and J2. I would look at, or I take the smaller of those two values, and I would take that smaller number and make that the exponent of this prime P2 in my GCD. And you do that with every other prime that's showing up. So we'll show you one sample here as to how we would find the GCD of two larger numbers. In the next video, we are going to do some more practice problems here so you can get a little bit more practice with that. So we're going to find the GCD of 194,040 and 737,110. First thing you have to do is write each of these numbers in its canonical form. 194,040 in its canonical form is 2 cubed times 3 squared times 5 times 7 squared times 11. And 737,100 in its canonical form is 2 squared times 3 to the 4th times 5 squared times 7 times 13. Now, for the purposes of finding our GCD, I could add at the end of the canonical form for 194,040, I could add a 13 raised to the power 0. And in the canonical form for 737,100, I could include here, again, for the sake of finding the GCD, I could include an 11 raised to the power 0. Just so that in each of these forms, we have the same primes showing up, and it's really easy and straightforward to then compare what exponents we should be choosing for these primes in the canonical form for the GCD. So my GCD in canonical form will contain each of the same 6 primes that showed up in both numbers, 2, 3, 5, 7, 11, and 13. Question is, what is the exponent that we are going to choose for it? So the exponent for 2, we look at the exponents on 2 in the 2 numbers. We had a 2 here and a 3 here. So I'm going to take that 2 because it's smaller, and that is going to be my exponent in the canonical form for the GCD. Next prime up, exponent for 3, I have a 2 here, and I have a 4 here. Smaller of those is 2, so I'm going to take that 2, and that's the exponent on my 3. And we do the same kind of thing. For 5, exponent of 1, exponent of 2, we're going to take the 1. For 7, exponent of 2, exponent of 1, we're going to take the 1. Here, 11, exponent of 1. Here, exponent of 0, we're going to take the smaller of those, which is 0. So that's why we have 11 to the power 0 here. And then likewise for 13, 13 to the power 0, 13 to the power 1, take the smaller power of 0 and write that in there. So this right here is your GCD in its canonical form. There we go. 2 squared times 3 squared times 5 times 7 times 11 to the 0 times 13 to the 0. And if you multiply those out, you get 1260. So this is a really nice way to come up with the GCD for 2 larger numbers. 6 digits, 7, 8, 9. The most pain in the butt part is coming up with the canonical forms for each of your 2 numbers on their own. But then once you do that, finding the GCD is pretty straightforward. But as I said, in the next video, we're going to do more samples of these, and we'll get more practice with these, and we'll see how this works. Now, if we had to find the LCM, what we learned earlier on in the course is that if you have 2 whole numbers, A and B, assuming they're both positive, the product of A and B is equal to the product of their GCD and their LCM. So once you have the 2 numbers and once you've found their GCD, you can easily find their LCM. So that is a lot easier to find what the actual least common multiple is. But tying in canonical forms, if you were to work with these same 2 numbers here of 194,040 and 737,100, you can find the LCM using that fact. And if you wrote that number in canonical form, and if you compared the canonical form of your LCM with the canonical forms that we found up top here, you should notice a bit of a pattern. You should notice that the exponents of the primes in your least common multiple are equal to the larger of the exponents on that same prime showing up in each of your 2 numbers, and that is always true. When you're finding the least common multiple of 2 numbers, A and B, the exponents on the primes is going to be the larger of the exponents associated with that prime in each of your 2 numbers. And that, if you think about it, it's not too crazy. It does require a little bit of thought, but it's not too bad to then see that that it does make sense that the product of two numbers, A and B, is then equal to the product of of their GCD and their LCM. If you write A, B, their GCD, and their LCM in terms of, or if you write each of them in its canonical form, you can see why the two things would be equal, and you can kind of see how that makes sense. But big thing from this video is being able to take a large number, write it in its canonical form, and then being able to find the GCD and then the LCM of two large numbers by using their canonical forms and using this fact that we talked about right here. In the next video, we're going to talk about a way to eliminate numbers as primes, as well as how to determine if a particular number is prime or not. And then we're going to go over the proof of a very kind of basic yet very important result about the distribution of the prime numbers. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.